Hello everyone. Today's lecture will be beneficial for the student of semester 4 physics honors, and it's about Heisenberg uncertainty principle and the determination of the position of a particle by using a microscope. Now, what we know about the Heisenberg uncertainty principle? Heisenberg's uncertainty principle. According to this principle, it is impossible to measure both the position and momentum simultaneously. Both the position and momentum simultaneously with ultimate accuracy. So Heisenberg has shows that even if you design an ideal experiment to measure simultaneously the position and the corresponding component of momentum, there will be an uncertainty, okay, in the position and uncertainty in the momentum, such that, now let us assume that if I consider an x direction, okay, the position rather x, then according to the uncertainty principle, we'll have delta x, delta p subscript x greater than equal to h by 4 pi. Here h is the Planck constant, what we know. And the product of the uncertainty delta x in the position of a body and delta px in its component of momentum at the same instant is equal to or greater than equal to h by 4 pi. Now, if one component is tried to be measured exactly, the other will become uncertain or completely uncertain, and vice versa. Okay, so this particular thing can be realized. This particular one, see, basically, it can be realized by using by a microscope rather. Now, what we do is that we'll take a microscope, okay, and we allow the electron rather, okay, rather we imagine we allow the electron E along the x-axis to move along the x-axis, and we'll try to find out the position and momentum of an electron, okay, using an ideal microscope. Now this ideal microscope, which we assume, now this has been focused, okay. Now what we do is that we'll try to focus it on the electron, which is incident photon. This is an electron and this is the incident photon striking on it. So this electron will get recoiled, okay, along a particular direction, and the photon is the scattered photon. Okay, what we assume over here is that in this particular case is this makes rather this part itself makes an angle theta. Okay, this is E electron which we have assumed. Okay, now this microscope, it is assumed to be free from all mechanical and optical defects. Okay, now what we know now is that, or rather we assume rather, that the particle were completely isolated. It is completely isolated. Particle is completely isolated from external influence. In this particular case, it's an electron. Okay, then the exact position, okay, at exactly measured time would give its exact velocity. Now but there is a problem that completely isolated particle cannot even be detected. So we need to eliminate it. Okay, Now what we know is that the limit of resolution okay, of the microscope is given by delta x is equal to lambda by 2 sine theta. Where lambda is the wavelength of light, here lambda is the wavelength of light. Okay, theta is the semi vertex angle of the cone of rays entering the objective lens of the microscope, obviously, and delta x, it is the order of uncertainty, order of uncertainty, okay, in the x component, obviously, x component of the electron. Now, the very act of illumination disturbs the electron because the light photon illuminating it transfer momentum to it. Okay, so the electron therefore recoils. Now, as per the Compton effect, we know already that due to photon, the electrons obviously recoil. The electron recoil because as the thing is that the electrons is in isolation, but as it is an isolated, it cannot be detected, so we need to eliminate it, and while elimination, the photon, because of the photon, there will be recoil in the electrons. Okay, now the electron recoils with change momentum. Okay, so the electron recoil with changed momentum. Okay, and any subsequent observation of the path of electron cannot tell us precisely what was its momentum before it was illuminated. So it is rather impossible to predict. So thus uncertainty is introduced in the measurement of momentum. Now the minimum amount of light incident on the electron is 1 photon, that we know. So the electron will be seen only when it scatters this photon into the microscope. So this photon has to be this photon, okay, the scattered photon. Only when it scatters into the microscope, the electron will be visible. The scattered photon can enter the microscope anywhere between the angular range, okay. The scattered photon can enter the microscope. Anywhere between the angular range, semi-vertical angle, that is semi-vertex angle, that is plus theta to minus theta. Now from the de Broglie relation, we know that P is equal to h by lambda. Okay, hence its x component. The x component lies anywhere. The x component of the momentum lies anywhere between the component of x component can lie anywhere between plus h by lambda sine theta, okay, to minus h by lambda sine theta, that is delta px. The uncertainty in the momentum is given by 2h by lambda sine theta. Okay, so this is delta x, delta px, and delta x already we have an idea. Now the product of the uncertainty uncertainties rather, okay, in the x component of position and momentum for the electron. Now will be given by delta x delta px is equal to lambda by 2 sin theta into 2h by lambda sin theta, which will be equal to h, which is obviously greater than h by 4 pi. So this is in agreement with the uncertainty relation. Okay, so this is the first part of the series of the lecture based on the based on the paper 9. I think it's for the CBCS syllabus of physics honors, element of modern physics. We'll continue the rest of this part of this particular syllabus in the next lecture. Thank you very much.